let's finish out chapter 10 talking about recurrence relations with generating functions. So if we have a recursive definition, and I'm just going to warn you ahead of time, this is a long process. So most of this video will be going over just one example. So here's my example that we're going to go over. And if you'll notice, this is not homogeneous. So I didn't actually teach you the other way on how to deal with non-homogeneous recurrence relations. We're just going to go straight to using generating functions. So what we want to do here is we want to find the generating function for this sequence given recursively. So it's given recursively, this is the recursive definition, this is the initial condition, so it's a complete definition. What we're going to do, just to make sure we understand where all this is coming from, is I'm going to write out the first few equations given by this function. So for instance, if I wanted to plug in, if a were 1 or n were 1, then I would say a sub 1 minus 3 times a sub 0 equals 1. And then what I'm going to do is I'm just going to take each one times x to the n. So essentially what I'm going to do is take this times x to the first. And this is the resulting equation. I'm going to repeat that process for n equals 2. So when n equals 2, I have a sub 2 minus 3 times a sub 1 equals 2. I'm going to take all of that times x squared. Here's my resulting equation. I'm going to do the same for n equals 3. That's times x cubed, etc. And we can see that if I got all the way down to n equals n, whatever n happens to be, I would take that times x to the n, and there's my resulting equation. Now, we're not going to have to do this each time. This is just so you understand where everything is coming from. What I'm going to do next is I'm going to add these up. And we looked at this before, and when we did this before, it was kind of nice because we had something like this where things canceled out. That's not what we have, unfortunately, in this case. So what I'm going to do is I'm really just going to combine all of these terms, and that can be written here as a sub 1x plus a sub 2x squared plus a sub 3x cubed, etc., etc., etc. It goes on forever. And I can further simplify that series to make it look like this. Essentially the summation as n goes from 1 to infinity of a sub n x to the n. And again, you can see that that pattern fits. Now I'm going to look at these values. Well, obviously the first thing that comes to mind is that there's a 3 in all of them. But again, I'm just going to list them out. And notice this minus, I just carried the minus over here. So now I'm saying 3a sub 0x plus 3a sub 1x squared. And this is how I would write it. And notice I've just factored that 3 to the outside. Then lastly, I would look at my last column, x plus 2x squared plus 3x cubed plus 4x to the fourth, etc., which I can write as the summation as n goes from 1 to infinity of n times x to the n. So far, I haven't done anything crazy. The crazy part comes next. What I'm going to do is I'm going to let g of x equal the power series. So g of x is going to represent the summation as n goes from 0 to infinity of a sub n x to the n. Now, looking at the 3 boxes, the blue, the green, the yellow, that I have, the 3 expressions, some of them are close to a sub n x to the n, some of them are not so close. So we might have some differences, like this guy starts at 1 instead of 0. And this guy has a little issue with n plus 1. And this guy, frankly, doesn't really fit it at all. So let's take a look at how we're going to tackle those 3 situations. So in my first part of my example, it's really close to my generating function, g of x, which is the summation as n goes from 0 to infinity. And really all I would have to do to make these two things match up is I want this to start at 0, which means it's essentially g of x, but I'm taking away a sub 0 x to the 0. Well, x to the 0 is 1, so really I'm just taking away a sub 0. So I'm going to rewrite my blue expression as g of x minus a sub 0, because now it's exactly what I want. Now let's take a look at the green. I've got the 3 on the outside, so I'm just going to leave the 3 out there. And the only issue I have here is I want it to be x to the n, and this is x to the n plus 1, so really I just have an extra x. So what I'm going to do is I'm going to factor out an x, and that's going to change that to just a sub n x to the n. So now all of the stuff in here is g of x. So I can rewrite that as 3x times g of x. Now for the yellow one, unfortunately there's nothing I can do in terms of g of x because it doesn't really match up. I don't have an a sub n, I have n. If you'll recall, back to section 9.2 video, when we first learned all about generating functions, again, I'm not going to go through the math on that one, but this guy can be written as the generating function x times 1 minus x quantity squared. I'm sorry, divided by 1 minus x quantity squared. So what I'm going to do then is on the next page, I'm going to take this equation and I'm going to plug in the 3 values that I have boxed. So by direct substitution, I'm replacing my first expression with g of x minus a sub 0, my second with 3x g of x, and my third with the generating function for that summation. From here, I'm just going to do some algebra. So it's going to be pretty straightforward. The first thing I want to do is I'm really trying to get all of the g of x's by itself. So I've replaced a sub 0 with 1 because I don't have it written on this slide, but on the last slide I specified that a sub 0 was 1. So I just did a substitution. Then I said, well, let's get rid of that. So let's add 1 to each side. Now on this side I didn't just put plus 1. I said, well, if I want to add 1, I'm really adding 1 minus x quantity squared over 1 minus x quantity squared, because that's just another version of 1. And I combined it to make it prettier. Notice on the left side that leaves me with g of x and minus 3x g of x. So I'm just factoring out a g of x from both of those, which turns this guy into 1 and turns this guy into minus 3x. From here, I'm just trying to get gx by itself. So I'm going to divide each side by 1 minus 3x, which gives me g of x on the left side. On the right side, the denominator is going to stay the same. The numerator, I went ahead and FOILed this guy out. 1 minus x quantity squared is equal to 1 minus 2x plus x squared. And so I'm then going to just combine like terms with the x that I already had up there. And so here is my generating function. Now, I'm not done. It doesn't factor, so if I were able to factor the numerator and be able to cancel some things out, maybe we'd get off the hook, but no, we can't. We're going to have to take this expression and do some partial fractions. So with my partial fractions, if you'll recall, what I'm going to do is I have 3 factors in my denominator, 1 minus x, 1 minus x, and 1 minus 3x. Because I've got a duplicate here, when I write the right side as the partial fractions, I have a over 1 minus x. Then I have b over 1 minus x squared, again because it's a duplicate. And then I've got c over 1 minus 3x. I'm setting that equal to that original function. Now what am I going to do? Well, I don't like fractions, so I'm going to get rid of the fractions by essentially multiplying everything by 1 minus x, quantity squared, 1 minus 3x. So on the left side, that's going to get rid of the entire denominator. For a, it's going to cancel out one of the 1 minus x's, but notice I have a times the other two terms. For b, it's going to cancel out both of the 1 minus x's and leave me with b times 1 minus 3x. For c, it's going to cancel out 1 minus 3x, which means I'm just going to be multiplying c by 1 minus x, quantity squared. My next step is simply to do the math. I FOILed this guy out, I FOILed this guy out, then I distributed a, b, and c. And then what I want to do is combine like terms. So I looked for which values have x squared. So here was 3a x squared and cx squared. So notice 3a plus c times x squared. Then I looked for just x's. Minus 4ax minus 3bx minus 2cx. So minus 4a minus 3b minus 2c times x. And last but not least, of course, I've just got a, b, and c, so plus abc. So what does this tell me? Well, the coefficient of x squared is 1, so I've made an equation. 1 is equal to 3a plus c. Then I looked at the yellow and said negative 1 is equal to negative 4a minus 3b minus 2c. And then I looked at positive 1 is equal to a plus b plus c. So again, you can see what I have is a system of 3 equations. As I said before, if you have a system or if you have a procedure that you prefer for solving a system of 3 equations, feel free to use it. I'm going to use matrices yet again. So again, from here, you're going to use whatever method you find best. I'm using the augmented matrix. I'm essentially using row operations, which is Gauss-Jordan method. I took you through this in great detail in video 10.2, the second half of it, or maybe the first half of it, I don't recall. I think the second half. Remember that my goal, if I'm using this augmented matrix, is I'm going to end up with my first row to be 1, 0, 0, and that's going to give me the solution for A. 0, 1, 0 gives me the solution for B, and 0, 0, 1 gives me the solution for C. So as you can see, I have shown what my row operations are, and I'm not going to spend 20 minutes talking about which row operations I chose or how I came up with them, etc. Because again, I went through this in great detail in just the last video right before this, the second half of 10.2. But what it comes down to is when I get to the end of the question, assuming I have this format, 1, 0, 0, 0, 1, 0, 0, 0, 1, those 3 values are my solutions. So what I did was I took my generating function, which I had previously, and remember previously this was an A, this was a B, this was a C, and I've simply replaced A with negative 1/4, B with negative 1/2, and C with 7/4. Now I am not quite done, so this is where I ended on the last slide. What I want to do now is let's go ahead and take these numbers, my numerators, and just put them to the outside. Let's just make it a little simpler. So that leaves me with 1 over 1 minus x, 1 over 1 minus x quantity squared, and 1 over 1 minus 3x. Now, if you'll recall, back in video 9.2, we spent a lot of time talking about generating functions and what their coefficients were, etc. So I went back in the vault from 9.2 and said, this guy is going to give me 1 to the n. That is the coefficient that I get for that generating function. This guy gives me n plus 1, and this guy gives me 3 to the n. So from here, let's just do a little bit of algebra. This guy can distribute, and then negative 1/4 and negative 1/2 can combine to give me my final solution. So my generating function will give me explicitly each value of my recurrence relation. So an explicit expression for my recurrence relation, which in this case is 7/4 times 3 to the n minus 1/2 n minus 3/4. Now, if you don't believe me, which you shouldn't because sometimes people mess up, let's go ahead and look at how do we check our solutions. To check my solutions, I'm going to first look at my recursive definition, and I'm just going to find, I already know a sub 0 is 1, so I'm going to find, say, the next 3 values. So using that recursive definition, and you can see I've already filled in the table for you, plugging in a1, so for obviously n equals 1, n equals 2, n equals 3. I'm looking at a sub 1 minus 3 times a sub 0, so notice I've just replaced it with 1, equals n, which is 1. Then I did the math and found out that a sub 1 is 4. To find a sub 2 is minus 3 times a sub 1, so notice I've replaced it with 4, and n is 2, so I'm setting it equal to 2. That gives me 14, and now I'm using 14 and using n is 3 and finding that a sub 3 is 45. So what does that mean? Nothing yet. Now I need to take a look at my generating function, which I spent so much time figuring out, and if they don't work out, then I did something wrong. So I'm just double checking to make sure I get the same values. So do I get the same values? Well, let's take a look. This guy, again, does not depend on the value before. I'm just using this function. 7/4 times 3 to the first minus 1/2 times 1 minus 3/4 gives me 4. Those match up. 7/4 times 3 squared, which is 9, minus 1/2 times 2 minus 3/4. Combine all those together, I get 14, which is the same as I got before. Last one, 7/4 times 3 cubed minus 1/2 times 3 minus 3/4 does in fact give me 45, which is the same thing I got before. So now I'm feeling pretty good about myself because I got the same value whether I use the recursive definition or my generating function. I'm certain after all of that you are just chomping at the bit to do another one, right? Because it was so much fun. That's why they call it Gen Fun, because it's just so much fun. So let's take a look at another one. This is a sub n plus 1 minus a sub n equals 3 to the n, where a sub 0 is 1, so our first term is 1. This time, instead of writing out the equations, etc., etc., we're just going to do it the cheap way, and the cheap way is to multiply by whatever the highest value of x to the n is. So really I'm just looking for the highest subscript, which is n plus 1. Notice I've taken everything times x to the n plus 1, and just like we did before, we're going to set g of x equal to our generating function, our power series. As we did previously, we're going to look at this generating function, the power series, and say, how close are we? If I took this and wrote it as a summation, and this guy and wrote it as a summation, and this guy and wrote it as a summation, how many of those meet exactly the power series, or can be written that way with some minor manipulation? Well, just as we did last time, if you'll notice, we've got the n plus 1 here, so we're just 1 off. So just as I did before, I'm going to subtract a 0. So by doing that, I essentially have g of x, and I'm subtracting a 0 from it. And again, just like last time, this one is off by just one x, so I'm just going to factor that x out, and that's going to give me minus x, g of x. And really, just like the last example that we did, this guy doesn't fit it at all. I can factor this x out, but then I'm left with that generating definition, x over 1 minus 3x. As I did before, I want to do a little bit of magic, move the plus 1 over, so that gives me this expression. I'm going to factor out g of x from g of x and x g of x. Then I'm going to get g of x by itself, and that gives me this. From here, as you well know, I must find some partial fractions. So again, I've got two factors, which means I've got two fractions, 1 minus 3x with a on top and 1 minus x with b on top. We're setting that equal to that original function here, and we're going to solve. So again, just as I did before, I'm multiplying every single term by that common denominator of 1 minus 3x and 1 minus x, which will give us varying degrees of things canceling out. So when I get to the bottom, I end up with 1 minus 2x equals a plus b minus a plus 3bx. So I've combined terms that don't have an x, I've combined terms that do have an x, and then I'm writing two equations. The first equation comes from 1 and a plus b. That's where this guy came from. The other equation comes from minus 2 and minus all of that. So notice I just dropped the minuses because that was redundant. So I have 2 and I have a plus 3b. So there's my two equations. Solve the two equations using a system of equations, and I find b is 1/2, a is 1/2. Plug that back into my generating function. Just as I did before, I'm looking at how can I replace, if I move this 1/2 to the outside, this is 1/2 times 1 over 1 minus 3x. What is the coefficient that I'm going to get? I'm going to get 3 to the n. Again, go back to section 9.2 if you forget where those came from. Same thing if I look at this guy is 1/2 times 1 over 1 minus x. 1 minus x I can replace with 1 to the n, so I did. Here's my solution, and then I just did some checks to make sure that I wasn't way off base. But here is my generating function, and that is my solution. So remember, if they ask me now for a sub n, it's equal to that generating function. That's what's going to give me my solution.
I did want to point out one other way that we can use with partial fractions in order to solve. And you'll notice this is the exact same example that we just went over. And what I've done is, instead of turning it into two equations, I kept it right here at this equation, which is what we've done just to eliminate those denominators. And then what I'm doing is I'm basically arbitrarily setting x equal to something. And I'm doing that based on the fact that I want this to be 0, so that I can basically eliminate the a and just focus on b. And then I'm going to make this equal to 0. And this works just as well as the other way that we have done previously. It gets a little bit trickier when you have 3 values or a repeated value, but generally you can still make it work. So notice what I'm going to do is one time I'm going to let x equal 1, and I'm just going to replace every x in here with 1. So 1 minus 2 times 1, so notice I just wrote 2. And then a is 1 times 1 minus x, so 1 minus 1 was 0, and of course that was the purpose, is I wanted this to be 0. And then b is 1 minus 3x, so 1 minus 3 times 1 would be negative 2, and then notice I still get b to be 1/2, and so I've replaced b with 1/2 here. And then I did the exact same thing with 1/3, so I let x equal 1/3. And then I had 1 minus 2 times a third, so 1 minus 2/3. And then a would be times 1 minus a third, which was 2/3. And b would be multiplied by 1 minus 3 times a third, which is, of course, 1. 1 minus 1 is 0. And that was the point, is for this to end up going away. And now I've got 1/3 equals 2/3 a. And then if I multiply each side by 3 over 2, I end up with a to be 1/2. And again, if you'll notice, that's the same thing that I had before when I did it the other way using a system of equations. And so all of this continues to be the same as the way that we went through previously, but this just gives you another way, especially if you get one of those tricky situations where you're having a hard time solving the system of equations.
Here's one for you to try on your own. This one should be fairly straightforward, the same methods that we just went through for the first two practices that we did together. So press pause, try this question in its entirety. When you're ready, press play to see how you did. Again, all I'm going to do is take each value times whatever my highest subscript is. So notice I've taken everything times x to the n plus 1. I'm still letting g of x represent just that power series. So this guy I could rewrite as g of x minus my first term. This guy, I just factored the 2 out, and again I had to also factor out an x, so this worked out nicely, so this would just be x to the n. So it's 2x gx. As before, I want to get all of my gx terms to one side, so I added a 0 to each side. I subtracted 2x g of x from each side. Then I factored out that g of x to get 1 and minus 2x, and then I divided each side by that, so here's g of x. This one I didn't have to do partial fractions on because I only had one factor in my denominator, so yay us, that's less work. I did, however, need to know all of that information from 9.2, so if you haven't figured it out, 9.2 is super important when it comes to generating functions. So I can rewrite this as 2 to the n. So really what I'm looking at is if I'm looking for the coefficient, again, a sub n, that's going to be equal to 2 to the n. And then, of course, I can do my checks to make sure that I am not completely in the dark and make sure that they match up. I've given you one more example to do, and I'm going to be straightforward with you. I'm not going to go through this guy step by step. I will uncover and show you all of the answer, so you can certainly press pause on your video once I do that and check over my work and look at your work and make sure it's the same. This one obviously is a little bit harder. If you'll notice, I have quite a few terms here. I've only given you that one initial value, which is all I need. But I've got just a lot going on. So do your best. This is a challenge question, so if you fail miserably, don't be too hard on yourself. It's not the easiest question. When you're ready, press play to see how you did. So I did warn you, this is a lot of work, a lot of fun, right? So the good news is I'm still following the exact same steps. So if you'll notice, I still started by looking at the summation of each. I replaced g of x where I could, which was not very often in this case. The other ones, 5 to the n and minus 2n, I just had to look at what those generating functions would turn into, again from section 9.2. And once I got down to it, down to here, that's when I started looking at using partial fractions to solve for a, b, etc., etc. So if you'll notice, I actually had to do a couple of different times. So why did I have to do it so many times? Well, because I had to figure out how am I going to write this. That's my number 1. Then I had to figure out how am I going to write this, which required me to do some partial fractions. That's all of my work for number 2. Then I had to figure out how am I going to write all of this, and that was my work for number 3. So like I said, this one was a doozy. When I put it all back together, I ended up here. So I did whatever I could to replace values, and then I just combined like terms. And so when I get to the end, here is my very, very final solution. If I need to find the coefficient a sub n, I'm taking 3 to the n plus 5 over n, 5 to the n over 2 plus n plus 1/2.